Hi scholars, welcome to session 8. Our main topic is withdrawal and reversal designs. The two main objectives are to 1. Describe components of withdrawal designs, and 2. Evaluate the difference between withdrawal and reversal designs. Let's start by showing what you know. Fill in the blank spaces in this definition of baseline logic. Blank measure of behavior using blank observation over at least blank adjacent conditions. The basic A-B design, also called a simple time series design or quasi-experimental design, introduces an intervention after stability in baseline is achieved. This design requires operationally defined behavior, data collection for at least 3 baseline sessions, and continuous data collection during the B phase. However, we cannot draw cause-effect conclusions because we need replication. An A-B design, therefore, offers no assurance that the change in the independent variable is responsible for the change in the dependent variable. Many threats to internal validity are left uncontrolled, for example, history, maturation, and testing. There are multiple threats to external validity as well. In single-subject experimental design research, our main goal is to establish causal relationships. This means that correlation, or an A-B design, is insufficient. At minimum, we want 3 demonstrations of effect at 3 different points in time. Experimental designs allow us the ability to demonstrate a functional relation. Some common types of single-subject experimental design include ABA and ABAB, hence our focus on withdrawal and reversal designs. Withdrawal and reversal designs require that we intervene on reversible behaviors. That is, we have to be able to demonstrate baseline responding under the non-treatment condition and show that it can be recovered again once the treatment condition is withdrawn. Some examples of when this might occur would be when we introduce and take away some form of compensatory support, or when we introduce and fade the use of response cards. For those of us intervening to meet academic goals, this is a bit of a challenge. Learning is not reversible for most participants, so once we teach a social skill using a strategy, we can't expect to simply fade that strategy and have the behavior return to baseline levels. It may not be realistic to expect that the student would unlearn whatever strategy they acquired. Once we've established that our dependent variable involves a reversible behavior, we might begin with a simple ABA design. This is similar to AB, but it requires the withdrawal of the intervention. As in the case of the AB design, we have to be sure to operationally define our behavior, collect data for at least 3 baseline sessions, and continuously collect data during the B phase with a minimum of 3 data points per phase. In the ABA design, B is introduced after stable baseline, showing either a 0 accelerating trend or a trend in the opposite direction of improvement, that is contratherapeutic. The advantages of the ABA design are that it's the simplest design that can evaluate a functional relation. We can control for threats to internal validity with this design. For example, we can control for history and maturation. If we plan to intervene on a different number of days in each condition, then we can avoid the threat of cyclical variability. We can establish external validity if we replicate the design with similar participants in the same study. With ABA, some threat and limitations remain. For example, there could be sequencing and carryover effects for which we would need to include multiple participants so that we could counterbalance or vary the order of conditions across students. 2 additional concerns are that some behaviors are impossible to reverse, and in some cases, it's not ethical to withdraw the intervention. The ABAB design is sometimes called the reversal design, the withdrawal design, the operant design, or the equivalent time series design. This is a powerful way to demonstrate experimental control. We can show immediate and abrupt change in level and trend. What we're looking here for is direct replication of effect. That is, we want to show behavior change upon introduction of both B's, and then we want the behavior in both A's to be the same. More replications equal greater confidence in our experimental control. Replication in this design is required across participants for external validity. When you use an A-B design, it's important to select and monitor behavior from the same response class. For example, if we want to focus on decreasing head banging, we'd also want to look at increasing the use of something like a slap bracelet. The advantages of this design are that it ends in a positive. The B is the intervention phase, and that's where we end. Intra-subject replication is possible with multiple demonstrations of effect across participants. So AB controls for a number of threats. For example, we use repeated measures and different condition lengths to control for history. We withdraw and reintroduce the intervention to control for maturation. There are no built-in protections for the threat of testing, but we reinforce the participant for completing the test in A and B. If we use reliable measures or have a really solid data collection plan, we can control for the threat of instrumentation. For the threat of adaptation, we might want to address this up front. Attrition remains a possible threat. What could you do to control for the threat of attrition if you're trying to establish external validity with an AB design? Reversal is a term used to describe this AB design when the intervention is applied to a different behavior in A2. Essentially, this requires monitoring two behaviors concurrently. When we withdraw the intervention from one of the behaviors, we apply it to the second behavior in A2. What we need are incompatible behaviors. For example, in-seat and out-of-seat behavior. Adult interaction when alone versus talking to peers. So I'll show a number of graphs that use this withdrawal reversal design, and we're going to rate them on a scale from 1, where there's no experimental control, to 7, where there's strong experimental control. What we want to use in making this determination is our understanding of the standards for single case design research, possibly from the What Works Clearinghouse, from Horner and colleagues, or from the NTACT evaluation checklist. So here's AB number 1. Rate on a level of 1 to 7, 1 being no experimental control, 7 being strong experimental control. I would call this one a 6. I see high level and baseline. The treatment shifts to a low level. We reverse that treatment, and it shifts to a moderate level. We reintroduce the treatment, and we shift to a low level. So let's rate that one as 6. There's fairly strong experimental control. AB2. Rate 1 to 7. AB3. Rate on the scale of 1 to 7. AB4. AB5. AB6. And finally, AB7. On this AB7, evaluate for both level and trend. So we want a score for level on the 1 to 7 scale and a score for trend on the 1 to 7 scale. Finally, take a look at this graph. What should be changed in this figure to meet APA guidelines? Name the first 3 things that you notice right away that you would change if you were going to make this graph conform to APA style guidelines.